So yeah, welcome to the hands-on part. It seems like people are excited about this, so that's fantastic. It's the stuff that Clint and I love too. So yeah, let's get going. The overview for today is basically we decided to break it up into two big sections. So part one before the break is really just about repeating a simulation, a standard, a standard simulation that we've made available, a standard experiment that we've made available, being able for users just to repeat that and then to be able to understand. Sorry, my slides are going forward themselves, but to be able to understand the output and verify that your expectations are met. Did we actually repeat the simulation that we thought that we were going to do? So that's what is going to be focused on in the first part. And I'm going to start that off by just talking a little bit about what our setup on Niagara is. Then in the second part, we're going to go a little bit more into the kind of intermediate content. So how we can actually start making changes to that configuration. We'll start with kind of smaller changes, and then we'll talk about making bigger changes that you would want to use version control for, and how you might go about that. So today, the guidance that we got from users early on was that we wanted a very kind of entry level walkthrough. And so that's what we're shooting for today. We don't have time to go into all the super advanced, you know, details about making big changes in the model. So that part is going to be saved for kind of future discussions, but we'll get you on a good path to starting off, hopefully. Okay, so let's just launch straight into that first part where we talk a little bit just about an introduction to CP4C on Niagara. So what resources? Okay, so we heard a bit yesterday that CP4C is a research platform to use CANISM external to Government of Canada. And we heard a little bit yesterday, and we'll hear more about CP4C tomorrow. But I just want to talk about it strictly at the kind of practical level. Okay, so let me put laser pointer. Okay, so CP4C has a resource platforms and portal allocation on Niagara of the Digital Research Alliance. And so what we've been doing is using the project space of the CP4C RPP to host required input files and libraries. And these are usable by anyone on Niagara. They're globally readable. This is just kind of public CCCMA information essentially. But we're storing it there on Niagara so that people have easy access for it. You don't have to download terabytes of stuff. Okay. CP4C members can access value-added services on top of that. So they can run jobs within the compute allocation of the CP4C RPP. They also have space where they can write content, including the RTD files to view in the browser. You have to be part of CP4C for that to work. You'll see what this means in a minute. And this is all subject to the CP4C policies and guidance. So, Paul will talk more about that, I think, tomorrow. But just to say that there is a bit of the separation. But even non-CP4C members, if there are people here that aren't actually part of CP4C, they should still be able to use the setup as long as you have access to Niagara. And by the same token, CP4C members can use this setup to run things completely under their own allocation, both compute allocation and storage allocation. So it's quite flexible. So yeah, today's content is really focused on using this, what we've set up on Niagara. In principle, you can extend this to other DRAC machines or to university clusters, or even if you had a big computer at home, you can probably run it. But we're not really going to cover that today. That's too advanced. We will make guidance for porting available in the future, but we're not going to cover that today. Okay, so this was kind of mentioned yesterday, but just to follow up on it because there were some questions. So the CANISM source code used on Niagara is identical to the source code used at CCCMA. That's for the model. But the supporting infrastructure used to configure, compile, and run the model in Niagara is different. Okay, and so Clint kind of alluded to this yesterday or spoke about it a bit. And Niagara uses something we call the Integrated Modeling System, or IMSI, and a simple shell sequencer. So the way that we run the model internally to CCCMA looks quite different. We have different technology that's basically some of it's impossible to port. So we're providing a slightly different system on Niagara, but it's also a system that we're going to move towards at CCCMA over the long term. So But anyway, it's in development, and it's not perfect, but it is functional enough, I would say, to do real science. And we've got examples. We heard a few yesterday, and we'll hear some more tomorrow. In order to support this, we're temporarily carrying a couple of CP4C branches to house these additional tools. And so, yeah, as I said, we'll eventually collapse down to just doing the same thing internally and externally, but we're not quite there yet. But at the same time, as we're carrying these CP4C branches, there's a lot of parallel development at CCCMA. So, yeah, there's a question yesterday about branching, and so I just put on this diagram just to indicate that there is a lot of parallel branching that goes on. And if you're just looking at this and thinking like, what the hell is this? It doesn't really matter. All you have to know is that when you come to use the code, you're going to be using this version 5.1 CP4C branch. Or if you really want to use version 5, you could use the version 5 CP4C. But that's what you're going to be using. And Clint will show kind of where this becomes relevant in his walkthrough in a few minutes. But yeah, at CCCMA, we are doing a lot of other parallel development that kind of interacts with this. And I guess we could talk about more, but really the point just here is that there are dedicated branches that carry all these additional tools, even though the source code for the model is identical. Okay, so this integrated modeling system is basically a new approach, and we're doing this to help us configure. We've got dozens of models, we've got hundreds of experiments for CMIP 6 and probably for CMIP 7, and we also now have this new challenge of offering kind of cross-platform support. So the old system and tools that we had for doing things were not really designed to offer all of that. And that's why we're kind of creating this new approach. So yeah, so CP4C has been a bit of a guinea pig in how will this work, and you're actually ahead of CCCMA in the sense of implementing this. So we also have this MZ program, which is kind of a single entry point command line interface, which gives users access to a host of setup, build, sequencing, and configuration utilities. And we use this kind of single entry point so that users can easily create reproducible simulation setups. So what this means is that by copying and pasting like basically 1 or 2 lines, I can guarantee that you will produce exactly the same simulation that I did yesterday or that Clint did last week. It's not dependent on human error of people copying files and trying to make sure they have all the right thing. That's not the way that we generally work at CCCMA. We have these single entry point scripts that let the machine make sure that you do everything the same way. Don't allow humans to intervene in that process because humans are too error prone. So Clint will demonstrate this all explicitly in a second. I just want to talk quickly about the resource requirements. So the first thing is compute. So by default, we're running the model on 6 full nodes on Niagara, which is 240 cores. And we're getting, okay, it says 15, it's 15 to 17 simulated years per day. So Jack Wong did a really nice project with CanESM a few years ago where we kind of like really went and tried out, okay, what is the best performance for expense kind of ratio or cost ratio that we can get on Niagara. And we basically, what we found is that essentially the lowest cost was using 4 nodes for the ocean model and 2 nodes for the atmospheric model. So that's this point here. And so that costs about something like 340 simulated or core hours per simulated year, and it gets about 17 simulated years per day. So it's kind of the best throughput to expense ratio is that one. But there are other options that people could choose if you want the model to run faster and be more expensive. Yeah, it's hard to actually get it cheaper than that, but that's you could use less if you wanted to use less nodes for some reason. You could use less nodes. Okay, so that's the compute, and then in terms of the space. So when the model runs, every user on Niagara has a scratch space. That has nothing to do with CP4C. That's the individual user has that, and I can't remember exactly what the size of it is. Maybe someone, yeah, it's in the docs, but everyone gets a certain allocation of scratch space. For running CanESM, I would say you probably need like at least a minimum of like 500 gigabytes free in your scratch space allocation to just allow things to cycle over. As the model runs, it'll produce 150 gigabytes about per year for the full output. That's kind of right as the model runs. And then as the diagnostic string kind of does the processing, which we talked about yesterday, it will reduce that down. It'll by default delete all of the kind of full what we call time series files, which are like super high, like 6-hour resolution, and it'll only leave that final CMORized NetCDF that we talked about yesterday. And once you've done that, currently that brings it down to about 32 gigabytes a year for the time series. Now, exactly how much that is depends on some options that can be set. Like, for example, if you decide to put out more ocean output, you could actually increase that number. But this just gives you an idea that doing that processing reduces the data burden down a lot. And but nonetheless, you still have to account for that. So when we run it, you'll see this accumulates in your scratch space. And that scratch space on Niagara gets wiped like once a month or something like that. So users have to manually move anything that they want to keep long term out of scratch space and into project space or into somewhere into their own allocation where they want to keep that, where they have space to keep that long term stuff. So that part is not automated at this time. Okay, so that's the compute, that's the space. Okay, and then knowledge. So basically for today, what we're assuming is that everyone has kind of like a basic working knowledge of like Linux shell, basically, that people are somewhat familiar with, HPC, submitting jobs and that kind of stuff. Those are all covered in, basic DRAC trainings. So we're not going to try and cover that stuff. And like really at the level of what we're doing, most of it today is like cut and paste. We've got instructions. If you can cut and paste those, it should basically work. That's for just being able to reproduce the reference run. That's kind of what we aim for, is this cut and paste ease. But then once we go into kind of really making changes to the model, then the requirements, the knowledge requirements about, knowing what's going on and how to use the version control and all of that, they increase kind of like there's a pretty steep learning curve there. And we'll start kind of showing you ways to approach that learning curve. But we're only kind of, scratching the surface of that today. That's what we have time for. So yeah. Okay, so just as a reminder, I showed this yesterday, but on Niagara, we don't have like every single thing that we have at CCCMA available. We've got two versions of CAN-ESM, 5.0 and 5.1, and we've got these experiments. So these CMIP6 experiments. So even though we ran like 105, I think, experiments in CMIP6, we haven't just made those all available on Niagara. Like people would probably not use them and it would be a lot of effort for nothing. So we've got these experiments available, and additional ones can be added, but the ones that we've added so far are ones that users prioritized. They told us, hey, these are ones that we want to use as base cases. So we've made those available, but additional ones can be done. Yeah. Okay, so we'll see that. Okay, and so then we did briefly talk yesterday about the GitLab space that has some resources. So I just want to quickly look at that, and then this project space that CP4C has. So will that... Let me open this up in my browser quickly. So yeah, if you go to that link, so there's this, everyone should be able to see this as it's just a public, basically, wiki on gitlab.com, CP4C. And okay, so there's a few things that I want to point out in here. The one is this quick start guide. That's what Clint is going to run through in a few minutes. And this is like literally where you're going to come and copy and paste essentially these. So that's there, which Clint is going to run through. Then a few things that we're going to come to later. There's a reference runs table, and this is showing the names of runs that have been done both in Environment Canada and that have been done on Niagara. And we're going to use these later when we come to look at the output. So that those reference runs tables are there. And there's also a link to this RTD browser. So yesterday we heard a few times about the RTD. And if we click on the link for this RTD browser, it opens up this kind of dynamic web page, and we're going to practically come and use this a little bit later. But I'm just showing you that link is on the wiki site for you to find it. Okay, and then the final thing that I want to say is just if you go into the repository of this project, there's actually a CP4C tutorial folder, and then there's some content here. These are the two notebooks that I'm going to kind of run through. And so people could download this, and you could like literally, these are executable. So you could run through it, and they've got a lot of notes in them. So you can practically download these and run through it like as we're speaking if you want, or at any later time, you can use them as a reference. So yeah. Okay. So I think we're pretty much right on track for the time. That's kind of an introduction to the resources. I'll just check in if there's any big questions at this point. Otherwise, we'll go on to doing the actual setup of reproducing a run. So any questions at this stage about just the overall resources and so on?